My name is Hashemi. I will be teaching this course. And as you see, the class is completely full. We have about 10 more students that they would like to come to this class, as well as we have some online students that they take the course online. So, and there are certain policies that I would like to follow. First of all, I will not tolerate anybody come to the class with the food. I'm allergic to the food, and if I see any food, and I get allergic reaction, so I appreciate if you have any food, eat it outside. And so there are some ethical behavior. If I see there are some violation, I'm not going to make myself nervous or upset and develop my blood pressure. I simply have your picture. I mark it down as ethical behavior, and you have 10% deduction and at the end for disturbing the class and do not follow the rule. So, but I'm not going to tell you anything. So you bring your sandwiches, you bother me, then I bother you at the end. And that's not, you wouldn't like that. The other thing is that I appreciate that you would not have your laptop and those things on in the front of you. If I see that your laptop is in the front of you and you are working with your laptop or your cell phone, again, that's ethical behavior. I do not tolerate that one either. So again, I'm not going to bring my blood pressure up and say that you guys are playing with your laptop or your cell phone. And under the table, I have your picture. I simply mark it down. So make sure you do that. The class is going to be on time. You would like me to be on time. And we appreciate it. You would be on time. So it's the same thing if you are in the airport and you are late. So they said, sorry, the airplane is gone. So now you have to pay some penalty. And those penalties in the form of the next time trip and extra fee. You have a dentist appointment, you have to be on time. The class is the same thing. You have to be on time. If you are late, I'm not going to bother you. But this time, I would not make a big issue out of that if you are late. So just make sure when you come here, just don't walk in the front of me. Go at that side and sit on behind at the end. I'm fine, as long as you don't make a noise. As long as you make, I appreciate if you are on time, but if it happens that you are not on time, I'm not a big fuss out of it. You lose yourself. You do not know what is the material that's covered. So please make sure that you are on time. And regarding the textbook is this book, which is a Fundamental Applied Dynamic. If you make a good notes in the class, you really don't need to read too much material. I make sure that we cover the material nicely, and hopefully you will be very comfortable. But this textbook is not available. I send you an announcement, and that you go on the Amazon.com or any other sources, you can get a hold of this book. There is also the 2 copies of this textbook in the library, which is my copies. I put in the library in the case that you do not have access. Please go ahead and read the reading assignment. So regarding the reading assignment, is all mentioned here. For example, let me see whether we can make this one a smaller magnification. So it's OK. Let me see whether I can fit them in one page. OK, here is better. Oh, that magnified that one. Let me see whether I can make this one a little bit. All right. It makes me nervous. So you do have a reading assignment. We have told you what pages you have to read. And you have the first problem set that you are going to be basically the due date. So we will not accept late homework. Now, let me be honest with you. I know the solution of these problems are available online or any other sources that you can hand yourself on. If you do that, that's not a problem. And if you would like the solution, you don't have to search it. Google it and go and find out where is the solution is hiding and so forth. Come to me. Don't go anywhere else. Come to me and say, I want the solution. I give you the solution manual, but I guarantee you, you will do very badly on the 2 hours exam, and you will do very badly in the final, and you will not pass the course because you haven't learned the material. It's like that you go to the army, and you would like to basically learn how to clean your gun. If you haven't done that part of it, and you go in the front of enemy, and your gun is jammed because you haven't learned it, the enemy is going to kill you. In this case, you get a bad grade. So I'm not going to bother myself. I know in the past, I had a student that they will go ahead and make a copy of the solution from some sources. They found it, Google it online, and textbook, sending email to the professor in charge of that he wrote this book, get hold of the solution. I'm not going to bother myself. You think that you secure 20%, but then you lose 80%. Decision is yours. You want to learn material, or you would like to pass the course. And if you want to pass the course with a decent grade, the honest behavior, I went to MIT. I had this course, and if you come to my office, more than happy to show you. Every week we had homework. And I never came to my mind. Of course, at that time, there was no online or Google it and so forth. We had to do it ourselves. And if you look at my homework, it's nice and clean. As a matter of fact, some student yesterday came to my office and said, Professor, I'm amazed with this homework, such a nice and clean homework. I said, I don't know. That's the way I was doing at that time when I was a student. So decision is yours. You want the solution? Copy from somewhere and pass it to me as your homework? Don't bother yourself. Google it. Come to me, and even you can come anonymous. I put the solution manual outside of my door, or solution of all of the homework outside my door. Come and help yourself. But if you do that, you will not pass the course. Period. So decision is yours. I'm not going to make myself nervous, and I'm telling you honestly what you should do, and that's what I hope that you do, and hopefully you would have fun. At the end of the semester, you say, wow, I learned a lot. That's what you would. And the class is large. So your homework is here, your reading assignments here, the due date is here, and then exam date is also mentioned. Exam number 1. Let me see. Exam number 1 is mentioned here, which is going to be October. Did I put a date? Oh, yes. Exam number 1 is going to be October 28. And exam number 2 is going to be on November 18. So I may change this one. But right now, that's the time that we are looking for, especially for the online students that they are working in the company and they may not be able to, they have to go some trips. Now they know the date. So, and that's as far as I'm concerned. So let me see. We have the reference book. Again, fundamental of applied dynamics. There are some suggested textbook that you can also go ahead and read. And hopefully you would have fun. Any question that you may have? Any question? All right. So as you see in the class, we have around 60 students. And I appreciate if you have any question, raise your hand, right, and talk to your fellow students. Oh, what's this talking about? Raise your hand. Maybe the same question another fellow student have. And so I would be more than happy to answer. More than happy to answer and entertain your question. Maybe we learn from each other. So let me tell you one thing. Education is like an ocean. It's like an ocean. It happens that I have 2 cups of that ocean. I do not know a lot of things. You may have 2 cups of that ocean as well. So let's share our cup together, so we make it 4 cups. So I learn something from you, you learn something from me, and we would have 4 cups. What's wrong with that? There's nothing wrong with that. So let's be happy, and we learn from each other, and so forth. The solution will be posted on the blackboard, and we have 2 TAs. We have 2 TAs for the course, and both of them, they took my course before, and they are well qualified to be a TA for the course. And let me see. OK, I take this one out. And they are my, oh, actually, I wanted to have this one here. Let's leave it this way. So we have a Surush here, and we have Mr. Yi here. And Surush, come here, please. So the online student can see you as well. And you come to you. So these are my two TAs. And Surush is going to be basically grading all of the homeworks that you pass on the due date, and he will pass it to you. The homework is basically a due date is there, for example, 23rd. The next Friday that you come to the class, you have to have homework with yourself. So you get a homework on Friday. The next homework is the following Friday, unless we announce it exception. But right now, that's our policy. And your first homework is on 23rd, due 23rd, and you will get the graded one the following week, and you would have the next homework due date. It's all mentioned on the blackboard. And Surush is going to grade your homework, and Mr. Yi is going to occasionally help him to grade homework. And maybe we would like to have some consistency, and consistency is in the form of that one student grade all of the homework. So all of the homework. For online student, please send your homework to you. Yui, why don't you write your email address? And online student, they send their homework to you, and he will grade it and make a PDF and send it back to the student online. So, and Surush is going to grade it in class student, and he will bring it here at the beginning of the class, and then he collect the. But online student, you don't have to send your homework. You send it as in the form of PDF to Yui, and then he will grade it and make a marking on the PDF and send it back to a student online. So, and if you do have a conflict that you cannot attend on this class on this time, you have other courses, then please register as online student. So that is basically would be better for the student. So if you do have a conflict, if you don't have conflict, stay here. That's not a problem. So, Surush, why didn't you write your also information? That is good enough. Next time you have to write it a little bit better. So I think it's good enough. Hopefully they can see that. And you can, I add your name in the blackboard, right? Yes. And you can send the email to the online student and say welcome to the class and so forth. And so we go from that. It's very hot and muggy today, isn't it? Why didn't you put your room number that you are located?
254 Regent.
So if by any chance that you somehow were not happy with the grading, or you thought that you did very well on the homework and the TA was, I already have told them, be nice, make sure, as long as the student have done honest work and you see the effort is there, give them good grade. So I don't want you to get discouraged. So I already have told both of them to be a little bit lenient, provided that you do honest work. If they feel that this is not honest work, they are going to be very harsh. So if by any chance you felt Mr. Surush deducted too many points for a small mistake, don't come to me. I have too many classes to teach this semester. I'm very busy. You go to the Surush and try to solve your dispute with the Surush. If he was not able to solve your problem, come and see me. I will meditate in between. But please try to see him, and that hopefully he will take care of you. So it's not going to be a problem. I will grade the exam as well as finals. So if you have a problem on my grading on the exam, come and see me, and I will try to accommodate you. I want you to learn the material. The bottom line is that I want at this end of the semester you say, wow, I learned a lot. And that's what I want to hear. And a student in the past has been telling me the same thing. So and hopefully that would be the case again this year. So as long as you do honest work, we do honest work together, we would be happy family. All right. Do you have any question from TA? There was a question from me, I guess.
That was for you, sir. Yeah. Are the videos available to us as well?
The video is also available to you guys, so you can, if you at some point you didn't understand, you can review the material again.
Okay. Thank you.
No problem. Yes, it is also available to everybody in the class. Any question from me or TA? All right. TA have any question from a student? Do you want to tell them welcome and nice to meet you?
Or just want to say something. If you want to meet me, I'm always here. But please send an email before coming to make sure I'm the best.
Same thing to you. Of course, you online student direct the question to his email, so you would have no problem. So, do you want to say anything to the student?
Yes. Welcome everyone to the class, and I think you're very lucky to have Professor Hashimi.
Well, thank you.
Me, myself,
I didn't mean that one.
I took this course last year with Professor Hashimi, and he did a very good job. So I hope you guys enjoy it.
Well, you should have said all of those things when I was not around here, so but that's okay. That's all right. Thank you so much, and we'll see you then. You can leave. Any more questions from the TA? All right. So let me pull this one down before we go further. And by the way, Yi is doing his master thesis with me. He's doing a fantastic job in the research. And so far, we have sent one paper for publication for master. One paper for publication. We have 2 more papers that we are submitting for publication. And I almost done one paper. He is looking at a rotating disk with a variable thickness with acceleration and on the composite disk that we have. So he formulated everything, and so he's doing a great job as well. All right, so let me just put this one on. All right. So why are we studying dynamic and vibration? So why are we studying that? So anybody can give you some idea why we are studying and why are you interested in such a course? Can somebody say? Yes?
And those things, there will be effect of inertia that we need to take into account.
Inertia that you have to be in account. That's right. So basically, let's say that you have my hand, and my hand is doing like this. At the same time, I'm doing like this. So you may be interested to see what happened to my joint. At this joint, as my hand is doing like this, and I'm bowing up and down like this, and you would like to say what is going on. And that is basically, that's what you are interested. So how do you go ahead to do this kind of problem? Or you do have a robot that it pick up some piece, does like this, and it rotates. Or you do have some MRI devices that it rotates, and at the same time it rotates that way. Or you have a camera system that is doing all kind of motion. You have to make sure in this design that you have that you, as a result of those motion, what kind of forces happening in each part of the system. So therefore, you cannot just go based on a static analysis and find what forces happening to the system. Or you may be interested, if you disturb the system, whether the system will basically go crazy from its equilibrium position, or whether the system is stable. So stability is also a problem. So if I'm sitting in the top of this chair and somebody push me, am I going to fall down and go crazy? Or I simply oscillate around my equilibrium position and come back to the initial position? So if you are interested in the robot or any devices that's motioning, you have to know some idea how to go ahead and analyze the system. How do you go ahead? For example, let's say my hand is here. I'm doing swinging like this. And and at the same time I'm swinging my back like this, and I'm doing some dancing. And I ask you, what kind of forces happen to my hip? What kind of forces happen to my joint? How do you go ahead and do that? And you just watch me. Yes?
Basically try to find the acceleration.
How do you find it? How do you do that? You, as an expert, this is me. This is me, and I'm doing all kind of motion, or this is robot, I'm doing all kind of motion. How do you go ahead and do that to find those things that's the acceleration and so forth? I'm just doing my hand like this. My hand like this. At the same time, maybe I'm doing like this, bending back and forth. So how do you go ahead? How do you do that? Yes?
Track the position.
Track the position. And what do you mean by track the position? Well, let's look at this picture. All of those things that you are saying is good. So you basically put a lot of marker in your body, and this is actually one of our research. You put a lot of point in a body, and you follow those marker by some camera system. So you do have some camera system. As the time goes on, you can see each point where it goes in a space in terms of vector. And if you do have a coordinate system, you can say what is the position of that particle or that pointer that is inside the body of this person. Where is that those point moves as a function of time? That's a way to do it. You have no other thing. And especially if you are interested to find, for example, as a result of this person walking, what kind of forces happening to the joint, the first thing that you have to do, you have to track the marker and get some idea about when I'm walking, which is called gait analysis. If I'm walking in this room and I have a force platform that I can pick up my reaction to the ground, as well as not only the reaction to the ground, as well as I need to have some information about basically those markers, how fast those markers moving, how much is acceleration, how much is angular acceleration, angular momentum, and so forth. And we talk about all of those things. So you have to have marker, and those markers, it is followed by some camera system. Camera system, like this. Then you do have, based on free body diagram, you do have ground reaction, and you do have all of those inertia that you have obtained by camera system, and then you can find what's happening to your joint. And once you have those forces to joint, you may do some finite element analysis or other thing to find out what is going on. And this is one particular person that we are interested. We were interested effect of the landing. So if the two hand is here, and she just like this, or the two hand is up and she does like this, what kind of forces happen to her joint? We were very much interested effect of the posture, the body posture. And this lady helped us to put a marker on her body and follow those markers, and also land on the platform. And then through that one, we obtain some information about her inertia, some information about ground reaction, and then through the free body diagram, we went all the way to her knee joint to see what's going on her knee joint, and effect of the landing. If her hand is like this, and she does like that, or her hand is up, land like that, what happens to that? There's lots of other things that you have seen that athlete with a bad movement, they rupture the ACL. So you would like to say, what kind of motion and how that motion affected ACL rupture? And if you can understand that, you can prevent. And we had a student that he did his PhD to look at it, what kind of the motion will lead to ACL rupture. So again, we had to do some investigation about ground reaction and so forth, and the motion. And then once we understood those things, we take those information and do FEA analysis. So you can see, not only we are doing in the biomechanics, you can think about it, anything. A car is moving, and at the same time is rotating, and your engine is going like this, and the car is rotating like that, what kind of forces happen to the bearing? So these are all important to understand. So that's the reason that we study those dynamic problems and try to, in the design, you have to know those things. So that's the purpose of this course, and hopefully we will learn from this. Question? Blackboard light off? Well, we need that one right now. I don't need this one, so when we need that one, so we can. Anybody else have a question? All right. All right. So when you are studying the dynamic, as I said, you have to have some marker. You have to have some marker and follow those marker. Follow those marker. And for that purpose, you can have different coordinate system. You can use Cartesian coordinate system. You can use cylindrical coordinate system. You can use a spherical coordinate system. You can use a path of the motion to somehow find out where is the object, where is your marker. So in the Cartesian coordinate system, that's x, y, z. And these are unit vector, I, j, k. Unit vector. And so the position of object at any time, you can say, I follow this RT and see where is the object at any time. And this vector has a component x as a function of time, y as a function of time, and z as a function. So the position of vector is defined as xt I, yt j, and zt k. So by finding how much is x at any time, how much is a y at any time, how much is z at any time, you can have basically an Excel sheet that says how much is x at any time, how much is y, and then you have an equation for x as a function of time. And same thing, you have some equation as a function of the t for y and z as a function. Now, if you would like to have velocity, velocity is defined how fast I change my position. So if at this time is here, next time my object, this is x, y, z again, and at the time t, my object is here. At another time, my object is here. You are following the marker, and you have a coordinate system. You can see how much is x at any time respect to that coordinate, like that marker. And this is r at the time t plus delta t. So the velocity is defined how fast I change my position. That means that my position is here. No, it has gone here. That's delta r. So the velocity is defined as delta r divided by delta t. And if you just go ahead and make a derivative of this expression, that becomes equal to dx dt I plus x di dt plus dy dt j plus y dj dt plus dz dt plus z dk dt. So for this Cartesian coordinate system, your I, j, k never change with the time. Never change. The value is 1, and the direction is constant. Never changes direction. So you can say that basically I do not have di dt, I do not have dj dt, I do not have dk dt, and velocity becomes simply x dot I, y dot j, z dot k. That's in Cartesian coordinate system, that's velocity. So if you do have Excel sheet, x as a function of time, you can easily find the velocity of the object of the particle. And of course, later on we go to the rigid body and so forth, that's different. But every particle, it has to be followed. And at any time you do not understand or you think something is not clear, please ask. So if you are interested, acceleration means that how fast I change my velocity. So again, if this is my coordinate system, x, y, z, and at this time, I'm going with this velocity in this direction, velocity at the time t. When I'm here, that's a velocity. When I'm here, I'm going in that direction. When I'm here, I'm going in this direction. So when I'm here, at the time t plus delta t, that's a velocity at the time t plus delta t. So if I ask you what's the acceleration, you have to say how fast I change my velocity. So basically, you make a parallel to the previous one, and that's delta t, delta v. That's delta v. So I'm having acceleration in this direction. My acceleration would be in this direction. And acceleration is defined as delta v divided by delta t, as delta t goes to 0. So you simply have to go ahead and make one more time derivative of this expression. And if you do one more time derivative of that expression, then you have acceleration. So acceleration becomes equal to x double dot I, double derivative of x respect to the time, x double dot, plus y double dot j, plus z double dot k. In Cartesian coordinate system. Very simple. Now you may have the situation that you don't want to use Cartesian coordinate system. It's not convenient for whatever reason. You have other coordinate system available to you. You can use cylindrical coordinate system. So let me erase this. Any questions? You may have cylindrical coordinate system. So your coordinate system is here. That's a coordinate. And the cylinder, and this is your particle, r as a function of time. And the cylindrical coordinate system basically is this r as a function of time, this angle phi as a function of time, and this length z as a function of time. So you do have three information. Like x, y, z, you have to have also three information. You have to know what's the phi or theta. Let's call it theta. I like theta better. You know that you have to know theta as a function of time. How much is the theta in the x and y plane? And this is x and y plane. And that's z. You have three things to be worried about it. And again, this is your vector. Again, you do have 3 unit vector. You do have 3 unit vector. Same like I, j, k. You also have 3 unit vector. When you define a vector, and you have to be good in vector. from your mechanics course, freshman in a mechanics course in your undergraduate, you have to be good in mechanics. You have to know the dot product, you have to know cross product. At the end of this class, I mentioned a little bit review of those things. But really, this is a graduate course. I shouldn't say it was a dot product, it was a cross product. I shouldn't go to the freshman physics and teach you those. But hey, I will mention. So, and you have 3 unit vector. And sometimes it's convenient to analyze the problem in terms of marker. When you put a marker, you follow those angles. You follow those angle and define how much is, when the point moves, how much my phi change, how much my theta change, how much my r change. When next time is here, object is here, for example, what is those angle, what is this one, what is r, and so forth. You should be able to mark it. And once you have a marker, you say, oh, at the time, 10 o'clock in the morning, this was the angle, this was r, a small r, and this was z. At 11 o'clock, this was r, this was theta, and I'm here right now, and you follow my angle respect to this room. So right now at 2 o'clock, for example, 2:15, my angle is this much, my r is this much, and now I go here, and maybe I jump a little bit. So my phi change, my r change, my z change. What a big deal. You make Excel sheet, you have all of those information. So again, you have 3 unit vector. The 1 unit vector is ER. 1 unit vector is normal to this one, E theta, and 1 unit vector EZ. So you have 3 unit vector, ER, E theta, and EZ. So now you would like to say, what is the position of vector? So position of vector, which is this one, r as a function of time. What is that? Can somebody tell me what's that? What is that position to describe it in terms of ER, E theta, and EZ? Like IJK that I said. What's that? RER and? That's it? Plus ZEZ. So you have to go this much vector, you have to go this much vector. So this is RER plus ZEZ. So that is the definition of the position of vector. And is R is a function of time, ER, Z, EZ. So if I ask you what's the velocity, again, velocity is defined. Velocity is defined as dr dt r dot ER plus r der dt plus z dot Ez plus z dez dt. So now you have to say, what is this? Well, the vectors Ez, it never changes direction. Always, no matter what's the time, Ez never changes the direction. So this number is 0. Never changes direction. On the other hand, you cannot the same thing for ER and E theta. So as this one rotates, ER and E theta change the direction. Although the value is constant 1, but the direction changes. Therefore, you cannot say der dt is equal to 0. You can say about the Ez, because Ez is always normal to this x and y, and no matter where is the object, Ez is always going that way. Never change the direction. So now you have to say, what is the velocity? So velocity becomes equal to r dot er. So you do have one component of velocity in the direction of r. So you do have one component of velocity in this direction, v, which we call it vr. Plus r. Now you have to say, what's the der dt? So again, you go ahead and add a 2 time to see what's a change of vector. Change of vector. So let's look at that one. Let's say this is my x and y. And this is my r. This is ER. And this is E theta. And that's a theta that I was talking about, x and y plane. Z is normal to the blackboard. So at this time, the vector ER is here. Forget about E theta right now. The vector ER is here. That's a vector ER with the length of unity. As the time goes on, the vector ER, it goes here. ER at the time t plus delta t. The length is 1, but the direction has changed. So now you can say, OK, what is the change of delta ER dt? So you can say, no problem. I make a parallel to this one, and that's delta ER. So the direction of delta ER, as you see, as the theta, delta theta goes to 0, is normal in this direction. So it is in this direction, E theta, as delta theta goes to 0. So that's basically rotation. So when you are rotating like that, so that's basically what you have. So it is normal to the delta ER as delta theta goes to 0. So what you have, this length of delta ER is equal to 1 times delta theta, that's a delta theta, 1 times delta theta, or 1 sine delta theta, which is small, and the direction is E theta. So delta ER dt is 1 delta theta E theta divided by delta t, and this becomes theta dot E theta. So we substitute for delta ER dt is equal to theta dot E theta plus z dot Ez. So you don't have 3 component of velocity in cylindrical coordinate system. One component of velocity is Vr, which is r dot. One component of velocity goes in this direction, like r omega that you have seen, r theta dot, and one component of velocity is z dot. So you don't have 3 component of velocity in that. One is the arm goes like this, r dot. One is rotating, r theta dot. And if it goes up and down, that's a z dot. That's z dot. You get 3 component of velocity. So r dot, like my hand, rotating, r theta dot, and it goes up and down, that's z dot. If I ask you what is the acceleration, and my delta ER dt from here was theta dot E theta. If I ask you what's the acceleration in cylindrical coordinate system, you say no problem. No problem. Acceleration simply is defined as delta V divided by delta T. So you simply have to go ahead and do one more time derivative of this expression. So this becomes r double dot ER plus r dot der dt derivative of this times this, derivative of this times this. And this has three terms, r dot theta dot e theta plus r theta double dot e theta plus r theta dot d e theta dt. And this would be z double dot ez. And of course, ez never changed, so I'm not going to bother myself. dez dt, it never changed. So now you go ahead and substitute. Well, from previous calculation, der dt is the theta dot e theta. So that is theta dot e theta. The only thing that's left was a det e theta dt. What is this? So again, you go to the same concept that we did before. And you can say, OK, this is my x and y. And this is my vector, r. This is er. And this is e theta. Next time, I'm interested in the det. So next time, my vector is here. It has changed delta theta, very small. And this would be er again. And this is e theta. So if I want det dt, so I have to make a parallel to this one, parallel to this one. And if I make a parallel to this one, is normal to this. That's that. Parallel to this, that's parallel. You see that? That's parallel. And so that is my e theta before. And delta e theta is this number. Delta e theta is this small vector. And the angle are mutually perpendicular. And that's a delta theta. And the direction of the det, direction of delta e theta, is a negative er. Negative er. This time is a negative er. So you can say delta e theta dt is equal to 1 times delta theta. The direction is er negative, divided by delta t. And this becomes minus theta dot er. So if you just simply substitute for this number, minus theta dot e theta, er, and put them together and simplify the expression, this has er, and this has er, this has e theta, and then you do have e theta and e theta here. And you do have also e theta here. So if you put them together nicely in the cylindrical coordinate system, so velocity was r dot er plus r theta dot e theta plus z dot ez. And acceleration, if you just go ahead and put anything has er in one parenthesis. This has er, this has er. You put in one parenthesis. That becomes r double dot minus r theta dot square er plus r dot theta dot e theta, r dot theta dot e theta. That becomes 2r dot theta dot e theta. And then you have r theta double dot. And then you do have z double dot ez. We will use this kind of equation quite a bit. Quite a bit, we use this kind of equation. So this two equation is very, very important in solving a lot of problems that we do in the class together. If it is moving just in the plane, then you do not have z. And z double dot would be 0, z dot would be 0 if it's moving just in the plane. If you have an object that is rotating, if you do have an object that is rotating, and let's say this is x, y, and z, and the object is rotating, that means a small rotation around the x, a small rotation around the y, a small rotation around z. So you do have delta theta x, you do have delta theta y, and you do have some rotation delta theta z. So it's like your coordinate system, basically, it has rotated. So you can think about it, a small rotation around that. Or you can say that basically this constitutes like a vector, as if the entire object is rotating around this axis. That's called angular velocity. And angular velocity is delta theta x plus delta theta y j plus delta theta z k. That's called angular velocity. As if the entire object is rotating around this axis. You don't have to say how much is rotating here, how much is rotating here, how much is rotating here. Entire object is rotating around this my thumb. So like that. That's called angular velocity. It's like that you go around the x direction, you go around the y direction, you go around z direction. Same thing with like a rotation. So you can think about entire rotation is going around that direction. And this is called omega x, omega y, and omega z. That's called angular velocity. Angular velocity. Now, let's say that we have a coordinate system here, x, y, z. And we have a cone here. That's a cone. That's a cone. And that's a cone like this. That's a cone. Think about it as a cone. That's a cone. Ice cream cone. And this ice cream cone is rotating around its axis, omega, angular velocity. It is rotating around that. So this is a cone that is rotating around itself. It's not going up and down, or it's not moving that way or this way. We can add that one in the top of that if we want. But it's simply rotating around its own axis. Now you make a marking here, and we can call this one vector A. Vector A. And maybe vector A is change its length in this direction. Maybe it changes vector A, it changes its length. At the same time, rotate with the cone. Just think about it. You have a ladder here, and you are extending the ladder here, and then you rotate the ladder. So we would like to know what is the derivative of this vector A. What's the delta A dt? That's a question. How much is that vector A change with the time? And vector A is just on the periphery. It doesn't go this direction. If it goes in this direction, then it is just sticking in the body of the cone. and the vector A is going like that. And the reason I'm giving you this problem, that comes to the next thing, that hopefully you will see that you don't have to go to the graphical technique to construct like a previous problem. I have to say, where is this one, where is the next time, and all of those things, and then it causes a lot of problem. You have to make a graph and see what the graph looks like, and then you discuss about that one, okay? And let's say that this angle of the cone is phi. The angle of the half of the angle of the cone is phi. So, and let's, for time being, let's assume A is a constant, so we don't have to be worried about the A never goes in this direction. But later on, I add that one as well, okay? And I'm interested to see what's a delta A dt. So how do you do that? How do you do that? How do you do that? Huh? Change. Phi doesn't change. It rotates. Okay? You are right. So you can say that this is here. Next time it goes here. Next goes here. And this angle is delta theta, which is with a rotation. With a rotation. And your A goes here. If I make it marking here, your A goes here, and that's a delta A. Delta A. Delta A. So think about it nicely. This is right here on the edge of the cone. No, it's a little bit behind the cone. It's a little bit behind. It, right now it's in the plane of the, let's say in the plane of Y and Z. No, it has gone a little bit behind the plane of Y and Z. And that is a like cone. So when I was a small child, I was making a lot of cone. So I'm sure you were making a lot of cone too, probably. That's your cone. This is a line here. And now you rotate the line here. Do I have a pen here? Yeah, I do have a pen. So one time it's here, my pen is here. Next time I rotate it, my pen is a little bit different. It rotates around the cone. So my pen is here, next time my pen is here. And so therefore, the length of the A is constant, but the position of A has changed. Like that ER and E theta that I was saying, same thing. So the question is that, what is a delta A? That's a delta A. So one time the vector A is here, another time vector A is here, the same length, and that's delta A. And it is normal to the, because it's rotating, it goes tangent to this circumference, basically. So what's a delta A? Well, you can say delta A is the length of this vector A sine phi, A sine phi, that is this one. This is a small r. Is a radius of that base. And that radius of the base has changed delta theta. Delta theta. That's a delta A. And the direction of that delta A is a normal to this page, because it goes like you open a page, you roll it, it becomes like that normal to the page. It's like my hand. So you can say it's normal to this one and this one. Divide by delta t. So you can say that is equal to A sine phi times delta t dt is omega. And the direction is normal to the page. Direction is normal to the A and omega. Because it's like that you open the page and it's like this. So as soon as you open the page, it's tangent to here in this direction, is normal to this one as soon as you open. So we are talking about the small. in this direction. This goes in this direction, tangent. So the value of the delta A dt is this one. And the direction you have to say normal to this page, which is contain omegas. So you can use the concept of cross product. You can say, and to achieve the same thing. So you can say delta A dt is omega times A. And this should be exactly the same as this one. So you do have a cross product. You have two cross product. And if you have two vector A and B, A times B is equal A times B, sine in between, sine phi in between. And the direction, you use your right-hand rule, and you go from A to B, and you can see what direction is that. So you can say this is equal to, you use your right-hand rule. If you do have two vector, this is A, this is a B. And you can say A times B, and this angle is a phi. A times B, cross product. A times B is equal value of A, value of B, sine in between. And the direction of that one, you go from A to B with your right-hand rule, and that's normal to the page of this A and B. Normal to the page of A and B. So, and that's normal to this page. That's A times B sine phi. So if you just do this operation to this omega times A, we would like to see if we end up with the same thing. A times sine phi. So you can say, okay, this is going to be value of omega, value of A, and sine in between. And the direction of that one is omega times A. So you have omega times A. You go here, this is vector omega, and this is vector A. You can see is normal to the page. Omega times A is normal to the page. And that is, we can say, E phi, whatever, is normal to the page. So you can see you obtain the same thing. Same thing, omega times A times sine phi. And the direction automatically comes. So whenever you do have a vector that's being twisted, you just use this number. And if the value of A is changing by itself, then you can say dE dt is equal A dot plus what is responsible for rotation? So let's look at that cylindrical coordinate system that I was talking to you. So this is my vector. That's ER. And that's my E theta. And that's my EZ. And the system is rotating around this axis. The system is rotating around this axis. It's coming out of the page, which is theta dot. So that's the theta. And if I'm using the theta, my system is rotating like this, and therefore my omega vector is in this direction, normal to the page. So you can say, okay, I'm interested delta ER, delta T. So you can say, no problem, according to any vector is equal to, because the length of the vector is constant, is omega times ER. And omega is theta dot EZ times ER. And EZ times ER, you go like this. That's EZ is here. EZ times ER is coming here. EZ times ER is E theta. E theta. That's a cross product. EZ times ER is in this direction. So that's the theta dot E theta. You don't need to go ahead and make a graph again, and you use this concept omega times A. Very important. You don't need to make any graph and so forth. Let's say that we are interested delta E theta dt. This one we obtain graphically. Now you can say no problem. This is ER. This is E theta. And EZ is normal to the page. So you do have 3 unit vector. Or you can say ER, E theta, EZ, ER, E theta, EZ. If you go in this direction positive, you go in this direction negative. That's cross product. And you get a vector, cross product. So you can say, what is the ET? Again, is omega times A. Omega times A. Because we show you with the cone, and no matter what the omega direction here is, that's omega times A. So you can say delta E theta dt is equal to omega is a theta dot EZ omega, that's omega, times A, and A is E theta. So again, EZ times E theta, EZ times E theta, you go in this direction, is minus theta dot E theta, ER. All right. So this is a very important thing. If the value of A is not changing itself, then no A dot. But if A is also changing, it extends as well as rotate. And that rotation, because the position of vector changes, you don't have to make a graph like a cone. Where is A this time? Where is A next time? What's the delta A here is, and so forth. You can simply use this equation and find what is the derivative of that vector. All right. Let's give you an... let's say that you do have a... that's a capital XYZ. We have a platform here. You can think about like a platform. And this is like a page. And it has some thickness. And the top of that, we have some disk here. Is mounted on the 2. And this angle, let's say this angle is 60 degrees. And this object, a disk, is rotating along this surface. Is rotating in this direction, omega number 1. So you have a disk that's going like this, and it has angular velocity. The angle change in that direction that you have, that's omega. So it rotates around that direction. So you do have only one axis of rotation. And the whole system, it also goes around this direction, omega. Omega. So both of them are constant. Omega number 1 is constant, and omega capital is constant. We are interested to know what is the total angular velocity respect to the capital XYZ. What's the total omega? What is total angular velocity? And we want to know what is angular acceleration respect to the capital XYZ. Very simple system. And this angle is 60 degrees. And both of them are constant. Suppose you have put some engine is rotating like this. Well, it's rotating like this because my thumb is going like this, my thumb. You always have to play with your thumb. It's going like this. At the same time, it goes like this. So you do have two rotation, one like this, that is rotating like this. At the same time, it goes like that. So you have two rotation vector. So your total omega total is equal omega k plus a small omega number 1, and this direction we call it ER. You can call it anything you want, ER, or you can call it anything. But you have to know a vector. It is because it's a vector. So you have one rotation here, my thumb. You have to give a vector, and you have to define as a vector. So that's your total omega. And if you want your total omega, that is as if the system at this instant is rotating along this direction. Summation of these two vectors. Parallelogram. Not a problem. Now, if you want to know what's the angular velocity, do I have angular velocity? Angular acceleration. Do I have angular acceleration? Or I do not have angular acceleration. Both of them are rotating at a constant velocity. Do I have angular acceleration? Yes or no? Well, you just say that go ahead and make a derivative of this expression. And if it happens to be something is changing, then you make a change. So you can say angular acceleration omega dot vector total, that's angular acceleration. This is constant, the k is constant, nothing. This is constant, nothing. This one, it goes around. It is sitting in the top of this platform, it goes around. So you can say omega 1 times der dt. And this direction doesn't stay constant. This direction goes around. It just rotates around. So therefore it changes. So therefore, what is responsible for that change? Which one is responsible for that change? Which one? Big omega is responsible for that change, not a small omega. A small omega never changed that direction. Big omega is responsible. You have to know which one is responsible for that change. And we said that if we do have any vector changes, the derivative of that vector is omega that is responsible times a. And for this case, this one is omega k times ER. So you do have angular acceleration because the direction of your omega is changing, or a small omega changing. The direction of a small omega, as omega number 1, is changing. And what is this vector? Omega. So your angular acceleration is equal to omega 1 times omega, no k times ER. At this instance, when the object is in the plane of the y and z, can you tell me what is the k times ER? K times ER. What's that? What did it say? What did it say? K times ER? What's that? What's it K times ER? I'm asking you, young man. Minus x? Well, first of all, you have to say unit vector.
Yes,
You mean minus I, you mean.
minus I.
That's it? What does it say? So here you are. A times B is equal to value of A, value of the B, sign in between, and you use your right hand to see what's the direction of your thumb. Okay. So value of A, K, is 1. ER, 1. So that's K, value of K, 1, value of ER, 1, sign in between, sign 30 degree. Direction normal to the page of these two. And your thumb A to B, that you go K times ER, is negation of negative I. So this should be minus 1/2 times I. At this instance, which is in the plane of the Y and Z. At other instances, it's different. So that is very important to understand. So when we talk about angular velocity, we basically change the angle. The angle is changing respect to x-axis, respect to y-axis, respect to z-axis. For example, if you do have this object, the angle change, that says angular velocity. Angular velocity. The angle change, it has some rotation, and that angle change respect to the time is called angular velocity. Position is a linear velocity and so forth. That's a position, different position. But at the same time, this rigid body, it goes different point, but maybe also rotate. So here is here, next time is here, but it also rotate. So you have to say what's angular velocity. Or it rotates respect to x-axis, respect to y-axis, respect to z-axis, and the total rotation, you can say, is along this axis. All right? So with this understanding, this is my object. The angle is here. You make a nice marking here. Now next time you say, where is this marking? Where is this marking? And then you say, oh, next marking is here. Or the next marking, it went here. So then you can say it has rotated around this axis. So you can look at it, how much it has rotated different axes. So angular velocity is a little bit difficult to see. Linear, no problem. You can say it has gone here, it has gone here, it has gone here, it has come up. That's a linear. Angle is a little bit, you have to think about it. What angle means is a little bit difficult concept. In the page of the blackboard is easy. Then you can say if it rotates like this is easy. If it rotates like this is easy to visualize. But when it comes combination, then you have to add all of this thing and say the object has rotated like that. So it's three rotation. And the whole system has rotated around that. So this is easy to say here. Easy. It is easy to say here. It is easy to say here. That's a 3 rotation. 1, 2, 3. So 1, 2, 3. So 3 rotation around each axis. And then you can say the total rotation is like you take a ball, and you can say how much is rotation. And sometimes to identify this rotation, we use Euler angle. Euler angle. If the time permits, we talk about Euler angle, and we discuss about that one. So now let's give you I got distracted. I wanted to say something, but I distracted from this one. Okay, so I do not know what I was planning to say. I got distracted. But if you do have any vector, omega, or you have a vector that is changed, the direction by the rotation, you can say omega times A. All right, I remember what I wanted to say. All right, let's say that you do have a solid and you do have a small penny here, a small penny with the radius A. Radius A. All right, and this penny, and this one is a radius capital R. Radius capital R. And this penny rolls without a slip. Without a slip, roll without a slip, roll without a slip. Shh, roll without a slip. And it goes here. It goes here. And this angle, you have monitored this one as a function of theta. So you took your time, and you said, how is a theta as a function of time? Theta as a function of time. So you took your micrometer. As the time goes, usually it's at 30 degrees, then it's 15 degrees, then it's at 20 degrees, then it's and that's your time. So what's the angular velocity of a small disk? What's the angular velocity of a small disk? That's a theta. And the theta as a function of time, you know that then you can find angular velocity of the theta dot. And because you have a nice Excel sheet. And yeah. So, but the question is that what's the angular velocity of a small disk respect to the ground, respect to a fixed coordinate system? What is the and that is this. The question that what is the angular velocity of a small disk? So how do you go ahead and find that? How do you go ahead and find angular velocity of a small disk? Remember on the blackboard what I said? This is my blackboard here. And this blackboard, not blackboard, eraser, this eraser rotate. That is, if you know the time and how much it rotates, delta theta, delta t. That's angular velocity. If you know how much it rotated here, then is that. Then you want it here, how much is rotate. That's angular velocity. And I said angular velocity is a little bit hard to digest, but for simple axis, it's very easy to see. That's it. Or if it is here, then it's how much is this? Or it goes here, how much is that? Then you put them together, that's angular velocity. And I said, my whole system has rotated around this axis. Very hard to visualize, but that's what it is. All right. So if I ask you what is the angular velocity, based on this understanding, what's the angular velocity of this disk? How do you go ahead and find? And the radius of that small disk is A. Big disk is capital R. And you have to say, what's that? How do you go ahead? What do you do? What do you do? And again, think about that this class is like a history class. We have a friendly discussion. We talk about Donald Trump. Is he crazy? Clinton is a nice lady, or this guy is good. And we have a nice dialogue discussion, a friendly discussion. And don't think it's like a quiz. And we are going to have a friendly discussion. What is the angular? How do you go ahead if you are going to measure, if you are going to do some experiment in the lab? Forget about analysis. And we ask you, just go ahead and do an experiment and report it angular velocity. How do you go ahead and do that?
There are two components.
Pardon me?
I mean, there are two components for this rotation.
Right.
Yeah. First one is small disk rotate refer to its center, and another one is a small disk.
No, the big disk is fixed.
Yeah, but it's rolling on the big disk.
Okay.
Yeah.
How do you go ahead and then?
Okay, for the small one, the rotation angular velocity is r theta over a.
Okay.
Over the radius of the small piece.
And then?
And then since we have the theta t, so we could combine those two components and factor the velocity.
Excellent. Very good. Very good. But that's not the way I wanted you to tell me that. But that's okay. That's one way to do that. There is so many different ways that you can pray to God. Some people pray to God like this. Some people pray to God like that. It's all good way. There's no problem. No problem. Any way that you can do that is fine. But we wanted a little bit more scientifically thinking. What is the definition of angular velocity? What's the meaning of angular velocity? Is a change of what? Angle. Change of angle. Like that eraser that I said, change of angle. Right? Okay. So what do you do if you want to see what's a change of angle? What do you do? If you want to know what is my change of angle, what do you do to me? Huh? You put your marker. Exactly. You put some marker and you see where is that marker went. Okay? So let's put a marker. So let's put a marker here. And I put a marker like a heavy line here. Heavy line. That's my heavy line. That's my marker has gone here. That's my marker before rotation start. Okay? And maybe I can make a bigger picture, but I think hopefully it's fine. Well, let's make a bigger picture here, bigger. Then you can see that nicely. So make it a little bit bigger. Make it a little bit bigger. So hopefully that life a little bit easier to see. So that's my marker. That's my marker. That's my marker. Okay? No, it rolled. Where is my marker now? Where is my marker? Where is my marker? It rolls like that. Where is my marker? Where is my marker? Somewhere here. Right? Somewhere here. Like a tire of your car. So what is the angular velocity therefore? What's the angular velocity? My marker is here. So you have to say how much the angle change. So the amount the angle change is this much. That's angle change. Initially is here. No respect to this initial is here. So you have to know what is this angle. PC. And a PC dot is angular velocity. PC dot is angular velocity. That's angle change. So now let's go ahead and see what is that. So you can say, okay, no problem. No problem. So no problem. I have to see what's a PC. So you can say PC is equal to this total angle minus this angle. This angle is theta. This angle is theta. The lines are mutually parallel, and this angle is theta. So you know theta. So your PC and this total angle is basically the distance that this one traveled. The distance this one traveled is the same as this distance. So you can say that this angle we can call theta plus PC times A is equal to r theta. So the relationship between PC and theta becomes this. PC is equal to r minus A times theta divided by A. That's a relationship between theta and PC. So how much is that? So the angular velocity of the disk is PC dot, which is omega of the disk, is equal r minus A over A theta dot. That's a fundamental understanding. fundamental understanding what angular velocity means. Angular velocity means that how much my angle change. So you have to put some marker. You have to put some marker and follow the marker. And you can say, OK, my marker is here. No, my marker is here. What is the change of that angle? And the change of angle, you can say, is a PC. The question is that what is a PC as a function of theta? So you can say that basically theta plus PC times this r, a small a, becomes this arc, must be equal to this arc. Because that's the distance traveled, rotation, that it does, rotation. So this length must be equal to this length because of the rotation. The distance that went, it must be the same. So you can say PC plus, we are trying to find PC. Theta plus PC times A, that's arc, is equal to r theta. And now you find PC, the relationship between angle change and this angle change is equal to r minus a theta divided by a. Once you have that information, then you can say angular velocity, PC dot, is equal to r minus a over a times theta dot. Is that clear? That's the way to find angular velocity. Angular velocity, if you go in the lab and you said, this is my leg, is moving up and down like this, and I ask you what's the angular velocity, you said no problem, it's here, at this time it's here, next time it's here, how much angle change, how much was the time, and the direction of that one is normal to the page of this body and so forth. You can say it's normal to the body, and so that's, you give it direction, you use your right hand rule, how much you rotate. If I rotate around this axis, you can say I have another omega in this direction. So in this course, you have to be a little bit comfortable with vector algebra, because we do a lot of vector algebra. I used to didn't cover that one, but I find it some student comes from overseas, and they have very poor background in the vector algebra. So, and we have two things really to worry about it, because the rest is easy. A vector A times vector B is equal A times B sine in between, and is a normal to the page of this two. It is normal to the page of this two, and this is sine phi A, B, and is a normal to this page. That's a vector. You can also have the dot product, and the dot product A times B. That's a scalar. That's a value of A, value of B times cosine in between. And it's a scalar, there's no vector. So that is, for this one, and you can say normal to the page, you can say EZ, so you know there's a vector, EZ, or in this direction, what to call it, whatever you can call it. Doesn't make any difference. So you can, this method, you have to use your right hand rule, your right hand, and say A times B, and the direction come normal, and then you have to figure out where is that normal, what direction it is. All right? So if you do not want to use your right hand rule, then you can go ahead and say A times B is equal IJK AX AY AZ and BX BY BZ. Use this determinant type situation, and you can find A times B. I wouldn't recommend this one. I want you, as a graduate student, you say A times B, what's my direction vector? And then figure out where is your thumb is going, which direction your thumb. But if you are in doubt, you can do that. And if you are in the cylindrical coordinate system, you can put ER, E theta, EZ, and you can say AR, A phi, A theta, AZ. So rather than that, so you can use. But again, as a graduate student, I don't want to use this one. I want you to say A times B is A times B. Where is my thumb is going? What direction my thumb here is? And then you figure it out, the direction of your thumb. Dot product, no problem, there's no vector. And you can say A times B times this, or you can say AX BX plus AY BY plus AZ BZ. Again, I don't want to use expansion form. I would rather use this equation, A times B cosine phi. We can certainly use expansion form. So, but make sure cross product of two vector is a vector and is a normal to the page of A and B, and the direction you have to use your thumb. Last year I had a student and she had difficulties. I didn't know why she's in my class. So A times B is a freshman physics. The definition of A times B is a vector normal to the page of A and B. And the direction is normal to the page, and the value is this. Dot product is this. All right, so let's expand on that one. You can, so we talk about Cartesian coordinate system. We talked about cylindrical coordinate system. We talked about rotation. The system rotates around X. The system rotates around Y. The system rotates around Z. And omega, that means the total system is rotating around this axis. It's like X, Y, Z motion, as if the system moves in that direction. So same thing with the rotation. You can think about that whole system is rotating around that vector. Think about it. It's very easy to visualize this rotation. It's very easy to visualize this rotation. It's very easy to visualize this rotation. So you have three rotations. If you have all of those three rotations, you can say that is along some direction. The total system is rotating around that axis, which is this. So rotation is a little bit difficult to visualize compared to the linear motion. Linear motion is no problem. I go here, then I go here, then I go up. No problem, you can visualize. But rotation, you have to say, oh, it's a rotation. I rotate it here, then I rotate it here, then I rotate it here. And if I want to put all of those things together, how much is the final rotation of this object? You have to put something that you visualize. It a little bit more difficult to visualize. OK, so why don't we stop here? And it's at 3:15. And your reading assignment is on the page. And next time, we talk about a spherical coordinate system. Coordinate system. And then we also talk about auxiliary. And then we solve some problem from this. And before we go, this is all kinematics. No forces involved, just from the position. What is that? So what we are discussing is all kinematic right now. So that means we have a marker. We don't care what forces is involved. We just follow those markers. And from those markers, we can find velocity, acceleration, angular velocity, and all of those kind of things. And then later on, we go to the kinetics. And we continue on that. All right, we see you on next Tuesday.